Hello, let's talk about chess. And what do I mean chess? Well, let's take a look. We have two chess games. I won't tell which one is in which language because these two chess games are written in two different programming languages. They are compiled. One of them is in Rust and the other one is in C++. So this would be the video that I have put the most effort out of anything because I have learned Rust. Well, not for this video, I have learned Rust for myself, but if I know it, why not make a video? And so these two files were created a month apart, but this timing is wrong. I just recompiled one version recently because I forgot to do it back then. So I think you can guess based on the file size which one is Rust, which one is C++, but well, maybe we will see later. So let's maybe see how this game looks like. This is chess. I don't know how to play chess. I mean, I do know how the pieces move, but I do not know much more. I do not know the openings, so blah blah. And this game has pieces moving. It doesn't have checks, doesn't have checkmates, doesn't have castling. Pieces can move, and that's how it looks. So let's see chess A first. So this is how the game looks like. It has the same interface in both games. So we have nice Unicode pieces, and we have two colors, white and black. Here we have current move and we move. So how do we move? First we select a piece. So let's say select piece D2, that would be this pawn. And then from D2 we select the destination, so D4 let's say. And this is how we move a piece. So let's actually then move E7. So this would be here to E5. And one thing which is nice, we cannot move we cannot move a piece where it can't move. So let's move d4 to, let's say, c5, and this movement is impossible. We have movement failed. The reason the move is impossible. So this is how it works, and we still get to make a move. So let's actually make a move from d4 to e5. So we will take the pawn. And as you can see, we take it. And now black can move, and so we, for example, cannot also select the white piece. So let's select e5, and let's move it forward to e4. And wrong piece was selected. So we have pretty much the fail checks. We have also every piece movement. So let's move actually the black queen from the 8 to, let's say, g5. And as you can see, pieces can move. And let's lastly move the bishop from c1 to e5 to g5. And as you can see, we can make the movements. So this is how the game plays out, and it generally doesn't even have the end. So I did not program the checkmate, and even if you take the enemy king, you still don't win. I didn't program it, but it is supposed to be a very crude game just to show the differences between Rust and C++. And well, this won't be a lot of differences in such a simple game, but a lot of people say that Rust is the killer new language, and so well, we can really see in this video if that's the case. So we quit with QQ, and so we have a recent quitting game. Let's also see chess B very quickly. It works the same, but you have, well, slightly different interface. The black pieces are actually black, and then we have here the same stuff, so we can input what we want. We can move d2 to d4, so everything works the same. So we can also quit. Let's actually take a look at fail messages. So let's move a8 to a7, and as you can see, invalid position supplied right here. Let's actually try to select a wrong piece, so d4 to d5 and invalid piece selected, so we can quit and we get a nice message, thanks for playing. Okay, so that would be chess A versus chess B. So now let's take a look at the source code and see a few interesting examples. So I won't be talking over all the game's code because there's quite a bit of it. I will just talk about specific points. All the code is available on GitHub for download. So let's start with C++ because this is the chronologically first thing that I have programmed. And so first let's talk about the main function. We include clocale because we need to set the locale to get Unicode output. So that's the first thing. We don't have to do this in Rust, which I suppose it's nicer. And we will also talk about the pieces, how they are displayed. So let's go to source code for the display. And here I use whitechar. So this is the whitechar code for a king, and then I use an enum and I basically add based on that enum. So that's really nice that you can cast from enums to integers just like that. And then we print the symbol, and also if we get the other side, we just add to get the filled in type of a piece. So this quick note, because in Rust, if we take a look in Rust in the display, the piece source code, what we get just Unicode symbols written in the. Even I made a display. I implemented the display trait for the piece type so that it can be easily displayed. Okay. So next up is the structure here. We have board, display, and control. I know this is not necessary if you are programming a game in a terminal, but I wanted to. It is more useful when doing a game with a library, some GUI library. But I also made it here so that the people who taught me to program like this are happy and they won't tell me bullshit. But one thing which this has, which is impossible in Rust, is the fact that the display has a constant reference to the board, so it can just take a look what's currently on the board and basically display the state of the board. And if we go back to the control holds a normal reference to board, so it can mutate. This is a mutable reference to board. This is obviously impossible in Rust. In Rust, you can only have one mutable reference or many immutable references. You can't have both at the same time. One difference also is that Rust usually has a binary and a library crate. So I use the library crate and dispatch the game loop and the logic to the library crate. So let's follow. This is actually the main function. We take a mutable reference to board, and the display of the board is delegated to the board structure itself. And we do not have a control structure. We have a separate function. So here we have a query input function, which takes the input, but we will talk about the input later. And we do not really have a display structure per se. This is the function which displays the game, and it has the loop. So we do not have any other structures other than board. That's how it works because Rust isn't really object oriented. So that's the reason. In control here in C++, we have a display reference and a board reference, so that the control has the loop function which dispatches display and dispatches board whenever needed. So this is maybe a neat thing that you have everything under one class, but that really doesn't matter. It isn't that efficient maybe for terminal games, but again, I did it like this, so maybe I could add a GUI to this chess game sometime in the future. Alright, so for the next thing, let's talk about how the board is represented. So let's go to the board class and take a look here. We have an array of size 64 storing each piece like a chessboard does. Well, I actually know that the actual chess games you have and the chess engines which are available online don't store the pieces this way. They use bit fields and some clever magic. But I did not learn that. I just wanted to learn Rust and not how to program chess. So so I made an array of size 64, and here we also use the supposed scary memory and safety of C++ by making a pointer. Very scary, yes, very scary. So it will be an array of size 64. Let's actually look at the constructor. Well, we have a lot of code here in the middle. And here we have the constructor, so we make fields, a new 64 array of pieces, and a piece is a separate type. It's a separate class. It has its own enums for type and side. And here, nice thing to notice, we have a type of empty and side of none. This is different than in Rust, because in Rust we do not have pieces. Well, we also cannot have nested types, but I will talk about this later. We have types as a separate thing and side as a separate thing, and as you can see, there is no non-side and no empty piece, because the board here is an option on piece. So if the option is none, there is no piece. Here, this is explained in the comment. So that's the difference in the board representation. And what I also have to remember that I have to distract so I don't get a dangling so I don't get a memory leak. So in the destructor of board I delete the array in fields. So that would be that for the board representation. And let's now talk about nested types. So something which Rust doesn't have, and something which is quite useful in object-oriented programming. But from what I have learned, from what I have learned, in Rust the lack of nested types is not really a problem. It's just you don't do the same design patterns as in C++ or Java or any other object-oriented language, because Rust isn't about objects. So here we have a nested type. In board we have a field position. Why I did it like this? Well, because the field position on its own is meaningless, and I only use it here in the board to index, as you can see here, to index the piece array, the array of the pieces. So it only makes sense to include the field pos in the board. It doesn't really exist anywhere else. So it makes sense that it is inside and part of the board. As opposed to Rust, where this is not really possible. So we make a position struct, and then we make a few functions related to the position. So later we can use these methods to index into the board. And another thing, in Rust you don't really have the same way of indexing, which is quite bad, so I had to implement a conversion from pos to usize, and this is here. So from position to usize. But that's a minor difference compared to what I have in the piece class. In piece class I also have a type and side, and here in Rust on piece I just have it separately. I have the struct piece which holds type and side. Type and side are defined elsewhere. But again, this is not really a problem because what Rust has over C++ is modules. And because this is in the same module, it relates the code. And so if we take a look at scopes, so for example here, we have current move, piece, side. So it's almost like nested types. The way you reference, or like the way you access these structures, is by the modules. So here we also have piece side, piece type. This is the modules make the nested types not necessary actually, and I think it's a better approach. But it's a better approach for Rust as a language which is not object oriented, because had Rust had nested types, it wouldn't be as clean and concise as it is advertised. Okay, next let's talk about error handling. And well, what do you mean error handling? This is because how I programmed the control loop. So first I made this in C++, where I decided I won't really be checking for a lot of stuff. I will just do a try catch block, which will move the piece. So it tries to move the piece, and moving the piece can throw an exception, only one exception, about an invalid argument, and it also can do a what to explain the error. So let's take a look at move piece function, and here it checks for invalid arguments inside the function. I could check it somewhere else, but then I have this here that I have to run some code before running other code related to moving the piece. So I cannot possibly know if the piece movement is possible. Only this function knows it. And so I decided to throw inside this function. And later I basically catch it and print it to the user. So this is the way I handle errors in C++. Rust has error handling to the next level. You cannot program in Rust without handling some sort of error at some point in your life. And I have it here. So I have errors on querying the input. So if the input is weird. And I also have errors on piece movement. One thing which you might get discouraged by in Rust is that you often run code as a side effect of an error checking expression. What do I mean? This is the prime example. So I want to move the piece and I want to check for errors at the same time. And well, I could make I could program it a bit differently. So match board.move piece, and let me quickly do this. And fill the match arms. So I could do this, and okay with anything, I don't do anything. I think this is this. Okay, sorry. So if I get okay, I do nothing, and if I get an error, I print the error. So I could do this, and this again is this is a waste of space, really. So I've used the if-let statement, which is a better way of doing this. That's why Rust has this thing. But this is the problem. You run code as a side effect of checking for errors. This is how paranoid Rust is, really. So that's what you get. And so how the error checking works. The query input function returns a result. So either it's okay with something or an error. Here it's also like a Rust thing that you can return anything which can be an error, so a dynamic error. You can also return a specific type of error, which I will show later. I actually have it here, So I can return a post-parse error or a quit game, which is also an error here. So they both implement the error trait, so they qualify to be in this box of dynamic error. This is not necessary, but if you might return more than one error, then well, if you then you kinda need this, and this is what I did here. So Rust, in terms of error handling, has also this really cool thing. So you can read exact. So it reads 2 bytes into the buffer, and here I have the question mark operator. And what it does, if it's okay, then it continues. If it's an error, it returns an error. So it returns error with something. And if it continues, then it goes to parse position, and parse position can also return an error. So here we have result or error. Here I also check, here I have types of errors, and here I also check for quitting the game. So that's how it works. And this parse position also returns a result. So this operator can only be used on result, and I think also on option, although I'm not sure. But if the function returns a result, you can use this. And well, that would be this for error handling. In Rust, you just have to handle errors. There is no way that you don't handle an error, just like here. Read exact is a standard input function for the buffered reader, just like here. This is also a bit convoluted, the input in Rust. Probably there are crates that you can use which make this easier, but well, here it's a bit more involved, but also maybe a bit safer, just like Rust advertises. And here you just have to handle the error. What if it is not able to read from stdin? In C++, the program would probably crash. I did not implement anything because I wasn't required to. My standard input usually works. I usually have a keyboard connected, but in Rust, even if it always works, you have to check for errors. Alright, next let's talk about indexing. And what do I mean by indexing? This is indexing into the arrays. So here I'm putting pieces inside the board. So this is actually a closure, so an anonymous function which I have defined as a helper for filling in pawns. This is actually quite a neat thing in Rust, but well, whatever. I use the fields which are defined here as the array, and just as I said, an array of option on piece. And here I use the indexing to insert a position. The problem is that that array indexing cannot just take any integer. It has to take usize. Why? Probably for some error handling stuff. Just like I said, you have to be able, the compiler has to be sure that you are able to index the array with the number you have. So you cannot index with an I32, so a 32-bit integer. You cannot do that because there are no negative indexes. The compiler is unsure whether the number you pass it will always be an unsigned, and even then you cannot index with any unsigned because indexing arrays is platform specific, something which is maybe a bit of dark magic for some people, and also for me. I actually did not read how Rust implements arrays, but I would have to read the compiler code, which I am not too smart, and I'm not too sure that I will understand. So this is how you index in Rust, and to make indexing by position possible, I had to make a function add, which basically returns a usize. So that's how I index. Then if we take a look at C++, how do I index? I do have a field add method which returns the reference to a piece which is at the specified position. So I use column and row. I don't actually use indexing by the position. The position is like a helper struct, which I will show later. But because of how I programmed the game in C++, I did not make functions which take position. You have to destructure the position before you input it. That's because of this field add function, which which takes the position and destructures it further into an array index. And as you can see, also a char is a char. So it's we all know a character is an 8-byte. It's a 8-bit unsigned integer. So C++ doesn't give a shit. It treats it as an integer. But in Rust, I had actually quite a few issues with this. So as you can see here, for the function which turns the position into a number, I had to use some casting to U8 and then cast the U8 into usize, which was a bit of an involvement, and I had to be careful for a lot of cases so that I don't make an error while programming. And one more thing, board in C++, you can easily overload the indexing operator with any type you wish, and I could also do that in Rust. I didn't do it because I didn't need to do it. I don't actually know why I didn't need to do it. Probably. Okay. I do actually have a function which returns the piece at this position, and as you can see, it takes a position and returns and takes the position further to turn it into usize. So this is using a conversion that I don't know if I have shown it, but here if we take a look at position, this is a trait which can convert the position into usize for easy indexing. So yeah, I got a lot of trouble with making indexing work well, and I decided that in Rust I will implement it as a method and not as an operator. But I could also do it as an operator, with the problem that usually in Rust when you use the indexing, it is unchecked. So either it will work or it will panic. With methods, I can clearly specify that it returns an option, and so you have to handle the case when the option is none. And next, let's talk about operators, and we will start with Rust because it's very easy. So sometimes in the code I had to compare for example, the side. So in Rust, you have to explicitly either implement or derive equality. Types are supposed to be non-comparable by default, so we have to explicitly implement it, and Rust has some clever macro to implement these traits for equality for you, but it does not always work from what I think. So that's the thing in Rust. Here, for example, I derived equality also because it's very logical that you will compare the columns and rows. But what if you want to compare objects a bit differently? You also have the door open for this. In C++, custom types are not comparable by default, and there is no way to derive it automatically. So I use here an operator overload or of the comparison, and if we follow the function, we basically get the same code which I would write in Rust, so that's not a big problem, but it's a cool thing that Rust has it automatic for some types, and for some types it does not have it. For example, if we take a look at enums, enum is equal to something that's really easy, if enum type has type queen, it will be equal to another type with queen. In Rust, you have to explicitly enable partial equality for enums. That's something which I actually don't know why this is, but it is a thing and a minor inconvenience, if not no inconvenience at all, because of the uh, partial equality derive macro, which always works for enums, I think, unless enums have here an associated type which might break the equality. So I don't know if pawn with true would be equal to pawn with false. I actually did not check it, but I don't think I used this anywhere in the program. This is something to investigate actually, and good thing I have spotted it while recording. So, and speaking of enums with types, let's talk what it means. So here I have an enum which represents integers. In C and C++, you can only represent one type using an enum. So here I represent enums. I have an enum of integers, which is by default, but I put it here explicitly so that then we can compare to Rust. And what Rust has cool about enums is that you can have enums with basically void, enums with tuples, so you can have tuple of bool and let's say I32. You can also have enums with a structure, so let's get a structure of what? Let's get A, which will be I32, and B, which will be U64. And this is all inside one enum, and I think there is, I don't know, I think this is it, don't remember. But this is what you can do in Rust. So if then I had a rook, I can store data only for rooks. If I have, and I use this for pawns, to actually know if they had made their first move. So I encode this information in the type enum itself. So that is neat. And also it is neat that you don't need to write these closed parentheses. It is by default. And if you take a look at C++ with the first move, here there is no way to store the first move inside the pawn type of enum, so I have to put a separate boolean for every piece, no matter what, and I only use it for pawns. Next, you might have noticed that I have comments. This is unusual for small projects, personal projects, to have comments, but I have put them here to show one important thing, which is really cool in Rust, and I know it is not in C++ for a very solid reason that C++ wasn't basically this idea of commenting the code in this way and making documentation was not really around that time. So that's why we have to use these normal comments, and I've commentated every function, almost every, to show that this is how you document your code. And for example, if I were now to write some code, let's maybe check here, if and then field at, and my LSP actually shows what this is about. So it shows the comment, what it does. And so it is also true for other functions which have comments for them, and I can read them easily. So that's for C++. That's how you comment your code, and that's it. You have it commentated. You can also, I don't know, maybe there are some automatic tools, but if not, you can just you just have header files. So header files are basically, if you write them well, they are self-documenting, from what I think. If you write the code well enough, I'd say. But in Rust, you don't have header files. But you have special type of documentation comment, which is awesome. I think it's a really good feature. You can use these comments ahead of functions, and then you also have normal comments inside or anywhere you want. You have normal comments, and you have these comments to inform the user. And while I write code, so let's maybe write some code. Here, let's see, parse. Let's do parse pause. I actually do not have a comment for parse pause. Okay, let's see. What do I have then? What I could use? Oh, that's easy. Let's use here board print. Let's repeat board dot, and here we have nice comments. So performs a piece movement by, and you know you can read it. You also have formatting. So as you can see, R, this I formatted to display in a different color than normal. Here we have print, and we have something akin to markdown files, and you have a lot of explanations. So that is one thing, and you can scroll these, but all of these are short enough that you don't need to scroll. And this is how Rust is documented, and you have even functions, you have code snippets inside this documentation, something which is basically unheard of in C++. So as you can see here, I have a comment, and then I have an example with a code snippet here. And usually these are examples how to use a specific function. What's also really good in Rust is that you can do this cargo doc. And let me actually open this doc. Alright, so this is the doc. And as you can see, well, mine is quite lame. There's not a lot, but you can go to core, to board. And here you have, if you dig deep enough, you have a nice documentation with everything there is to know about a structure. So as you can see here, we can read what the add function does, what's this function's signature, so something which is somewhat in C++. It's not in a website form, and it's not a convention. it it just is. And here we have basically a header website which shows everything there is to know about the structure. It doesn't show private fields, which, I mean, is it really necessary? I don't know, because if you don't have you don't really use any private functions, so that is why you don't have it here, and maybe makes this makes this documentation less convoluted. So we can close this, and that's a really cool thing about Rust. Next cool thing is how you compile your project. In Rust, there is no build system. You just use cargo. You do cargo build. Your cargo build release. And well, there is some, I think you can put some options for compiling the release and blah blah. And then you can just cargo run and you get what you want. What's the difference in C++? Well, let's quit. And if I list the directory, I use cmake. So in C++ you have build systems. For this video I wanted to use GNU automake, GNU auto tools, but I decided against it because this is so complicated that I think only GNU packages use this, and some other maniacs which sit in compiling C all the time, so they know how to do this. This was actually my first time writing CMake code, so we can look at the listing of the CMake lists. So it's not a lot. I actually have the features which I will show later. You can read the code more, but I have a debug option, so I can put some configuration whether to enable color, so then I put a more preprocessor definition for color. Same for debug. If I have a debug configuration, I enable the debug macro. And so this is not a lot of code. Most of this is just checking for the necessary header files, and here it's just showing setting the correct compiler flags. This is I think CMake is even too complicated for this project, but I just said let's do this and let's not have any problems. And here you have a nice executable. This actually is really simple, and if I didn't add all these options, CMake would actually be really easy. So how do we compile with CMake? I showed how do we compile with cargo. How do we do with CMake? Well, with CMake, you do this. And actually, would be nice to remove the file. So remove everything from this directory. Okay. Error. What? Okay, doesn't want to get removed. Whatever. Let's run cmake, and we get cmake, and then we can do ninja verbose. Because it did make. So we can compile, and it is all compiled now. So if I check, we get cpp-chess, and we get the version of cpp-chess. So as you can see, compiling with cmake is a bit more involved. You can also set the generator to ninja, I think. So if I personally prefer ninja, so we can do this, and then we get ninja like this. So this is all these nuances and the decentralization of C++, which makes it harder to compile. But all in all, I think it's good that it's not centralized, because if the central system turns out to be shit, you can always use an alternative. In Rust, if they make something shitty, a shitty decision with cargo one day, there is really no way to use anything else. But one cool thing about cargo is that it knows about every single file you have put in your project, so you don't really have to care about the compiling process. You just write code and that's it. And as the last part of this video, let's actually talk about which one is which. So chess A was in Rust and chess B was in C++. This big file size, why is that? Well, Rust statically links executables. This is in one way good, because makes it easier for cross-platform development, but also is bad because of the file sizes. I don't know if there is a way to link dynamically with Rust, but Rust does produces big executables. Also, this might be because a lot of Rust is generating a lot of code. So you have in Rust, you don't really write a lot of code. You have a lot of syntax sugars, as I've said, as I've demonstrated with the if-let example, that you can write cleaner code. But after all this clean code, it just gets expanded to the basics and then gets compiled. C++ is linked dynamically with the standard library, and so it only works on my computer because I compile my system with LLVM, so if even if I transfer it to my laptop, it wouldn't work. And with the Rust application, I'm pretty sure it will work on any Linux distribution which has the necessary capabilities of running this software. And so that would be it for this video. I thought it is not too boring, maybe 30 minutes of me talking, but all the code is available on GitHub, will be linked in the description. And that's it from me for today.